This is the third lecture about cardiac output, blood flow, and blood pressure. The average cardiac output at rest for an adult is about 5 liters per minute. And we can see in this diagram that there's an unequal distribution of this cardiac output to various organs. So here's a person at rest. They're generating 5 liters per minute. So about 20 to 25% of the blood goes to the liver and the gastrointestinal tract. 4 to 5% goes to the heart, 20% to the kidneys, 3 to 5% to the bones, 15% to the brain, and about 4 to 5% to the skin. And finally, at rest, about 15 to 20% of the cardiac output goes to the resting muscle. Now, note there's a few standouts here. For example, the brain is only about 2% of the body by weight, and yet it receives about 15% of the cardiac output. So this gives you an indication of how metabolically active the brain is. It has a very high metabolic rate relative to certain other tissues. And the kidney also is a very small organ. The kidneys together are very small compared to the rest of the body. They only account for about 0.5%, so 0.5% of total body weight. And yet at rest, they account for 20% of the blood flow. And this makes sense because, of course, the kidneys filter the blood. This is a table giving the total percentages, which are very similar to the diagram that was just shown. Note that this person's slightly larger. So instead of 5 liters, this is 5.8 liters for this person for the total cardiac output. In order to understand blood flow in the human body, we need to understand the basic physical laws. First of all, blood flows from a region of higher pressure to a region of lower pressure. The rate of blood flow is proportional to the differences in pressure. So for example, if we have a tube and we have a certain pressure P1 at one end and another pressure P2 at the other end, then we'll have a difference or delta P between the two ends. If we imagine that P1 is greater than P2, then we know that the flow will go in the direction from P1 towards P2. We can take that tube that we had in the previous slide and imagine turning it into a circle. So we start now at the left ventricle where blood is ejected through the aorta from into the blood circulatory system. The blood then travels through the systemic circuit coming back to the right atrium. So what drives this blood flow? What's the pressure, right? And the most significant pressure will be the mean arterial pressure. So we'll assume that that's 100 millimeters of mercury. And by the time the blood gets to the right atrium, it's effectively about 0 millimeters of mercury. And therefore, our delta P is 100 minus 0, or 100 millimeters of mercury. For this reason, for all our subsequent calculations, we'll take MAP to be equivalent to delta P. And this is because the pressure is so low in the right atrium that we can effectively say it's 0. And therefore, MAP is in fact a delta P. Before we move on, we should define things. So when we talk about flow rate, we're talking about a volume flow rate. So a volume flow rate of a fluid is defined as being the volume of fluid that is passing through a given cross-sectional area per unit time. So imagine you're standing next to this tube and you're looking at the amount of volume of fluid that goes past this particular point. And you have a timer and you measure for 1 minute. You say, okay, this volume is past beyond this point in 1 minute. Well, that's your volume flow rate. A certain number of liters has passed through the tube per minute past that exact point. So the reason I'm stressing this is it can be quite easy to get confused and think about velocity. So velocity is a completely different measure of what's happening with the fluid. It's a speed. So velocity is a distance per unit time. It has nothing to do with volume. Okay. So now that we've gotten that out of the way, the rate of blood flow is directly proportional to delta P. Therefore, the difference in the higher the delta P, the higher the blood flow. So we could think about the circulatory system. The higher the mean arterial pressure, we can imagine if the right atrial pressure is always 0 millimeters mercury, that would correspond to an increased flow rate potentially. Okay, so then The rate of blood flow is inversely proportional to the frictional resistance to blood flow within the vessels. So we get this basic equation, which we'll use over and over again, and we'll see in different forms. But blood flow rate, again, that's the volume flow rate, so say liters per minute, is equal to delta P, which is the difference in pressure, divided by the resistance to blood flow within the vessels. And that resistance we can think of as mainly being due to frictional resistance between the moving fluid and the stationary walls of the tube. There's of course also resistance due to the within the fluid itself, but that's a smaller component of this resistance. Okay, let's take a look at an example, and I haven't given you the formula or anything. I just want you to try and guess when you look at this. If P1 and P2 are the same in both blood vessels, so now we have two blood vessels, but the second one is twice the length of the first. What will the rate of blood flow in the second vessel be compared to the first blood vessel? So the potential answers are 25%, 50%, 33.3%, and 100%. The answer is that the flow in the second blood vessel will be 50% of the flow in the first blood vessel. And this seems surprising because all we've done is double the length, but think about the origin of the resistance. The resistance has to do with the interaction between the moving fluid and the stationary walls. And so if you've doubled the distance over which that interaction could occur, then you should double the resistance. So that's in fact exactly what happens. And as we'll see in the next few slides, this is something that's been worked out, and so we have an exact formula. As a quick reminder, we had this original equation, blood flow equals delta P over resistance. And that's why we're so interested in resistance, is because it's going to help determine blood flow, say, through an organ such as your brain. So resistance is measured as this. So resistance is proportional to the length of the vessel multiplied by the viscosity of the blood divided by the radius raised to the fourth power. Okay, let's do another problem. If P1 and P2 are the same in both blood vessels, but the second blood vessel has twice the diameter of the first, what will the rate of blood flow in the second blood vessel be compared to the first blood vessel? The answer is that the blood flow will be 16 times greater. If we look at the two formulas that we used before, we can see why. So let's imagine we had a doubling of the radius. Well, this means the resistance would now be 1/16 of its original value. And so now blood flow is going to be equal to a certain pressure difference, right? A delta P divided by 1/16. And so that means the blood flow would be 16 times greater. If we combine the two formulae in the previous slide, we then find a new formula, which is blood flow equals delta P multiplied by the radius to the fourth power multiplied by pi divided by the viscosity divided by the length and divided by 8. Note that there's some extra terms here in the pi over 8. And this is because before we're just showing the overall idea, whereas here we're actually showing the exact formula. So this was actually exact values that were determined empirically by Jean-Louis Poiseuille. He was a physicist and a French physician. And so he actually ran lots of different fluids of different viscosities and so forth to mimic blood through lots of tiny tubes and measured these empirically. And so he arrived at this formula. And so this is if you actually wanted to know exactly what the blood flow and you had the radius and the viscosity and so forth, you would put all these things in and you'd get the actual value. But the main point for us is to just look at the overall idea here. So if we have blood flow, which again is a volume rate flow, it's going to increase if the delta P is larger, which makes sense. If there's a larger increase in radius, remember if we doubled the radius, then this would be 2 raised to the fourth power, so that would be 16 times higher. So we'd have a 16 times higher blood flow. So those things could change blood flow. So increase in pressure, increase in radius of the tube will increase blood flow. And if we look at what will decrease the blood flow, well, an increase in the viscosity will decrease the blood flow. Let's say we doubled the viscosity, well, then the blood flow would decrease to half. Let's say we doubled the length of the tube, which we did earlier, then that would decrease the blood flow rate to half. And so those are things to keep in mind as we discuss what happens within our body. So when we have vasoconstriction of arterioles, that's going to decrease the radius, and therefore that will increase the resistance to blood flow, and the blood flow will go down. Conversely, you could have a dilation of an arteriole due to the smooth muscle relaxing. That would increase the radius of the arteriole, and that would increase blood flow. And so it's through a pattern of vasoconstriction and vasodilation that our body is able to direct blood flow to different organs at different times. This figure illustrates the principle I just outlined. Let's imagine we have arterial blood flow coming in this way, and we have a split or bifurcation in the blood vessel. And here we have a radius of 1 millimeter for this tube, this vessel, and we have a radius of 1 millimeter for this blood vessel here. So as you can imagine, you'd have about the same blood flow, or F, for both of these. And we're going to have the same resistance. We'll just call it R for both of these tubes. Now, let's say, imagine that we increase, we have the same arterial blood flow, but now we increase the radius of this blood vessel. Well, the resistance will now be 1/16, right? So we have 1/16 of R, and this means the blood flow will be 16 times higher than what it was previously. So we have an increase in blood flow. Now, with this other tube, we're going to decrease the diameter of or radius of the tube from 1 millimeter to 1/2. Therefore, the resistance now goes up by a factor of 16. And now the blood flow is really much lower. It's now 1/16 of what it was originally. So you can see these are sort of exaggerated examples. I don't think any blood vessel would really change this much in diameter. I suppose it's possible, or this much in diameter, but typically you have a little bit smaller changes, and yet you'll have very large, the main point is a small change in diameter will lead to a very large change in the blood flow. This figure shows the pressure differences as we go through the circulatory system, starting at the left ventricle to large arteries and so forth. Notice that, first of all, the pulse pressure, which can be seen in the large arteries, essentially dissipates by the time we get to smaller arteries and arterioles. So this is important because we really don't want pulsations of blood pressure by the time we get to organs. That could damage the organs. And by the time we get to capillaries, you see there's pretty much just a steady pressure, which is good. The other thing you'll notice about this diagram is that the pressure decreases most dramatically around the time you get to small arteries and arterioles, and then furthermore as you get into the capillaries. And so this decrease in pressure is a function actually of the resistance of these small arteries and arterioles. So these So remember, you can think of pressure as kind of like a potential energy, and it can get used up due to the resistance that occurs between, due to the friction, which is due to the interaction between the moving fluid and the stationary walls of the tubes. And so really when you're in the larger tubes, there really isn't much decrease in pressure because there's hardly any resistance. By the time you get to the small arteries and arterioles, then there's a pretty dramatic decrease in pressure, and that's because there's a lot of resistance. So sometimes these arterioles are thought of as sort of resistance vessels because they present resistance, and that resistance, furthermore, is variable. And this variable resistance allows for blood flow to be directed to various organs. So less resistance would correspond to a higher flow to a certain organ, and a greater resistance, which would happen with vasoconstriction, would lead to less blood flow through a particular organ. Okay, now the next thing we're going to look at is total peripheral resistance. Now this term encapsulates essentially, it's the sum of all the vascular resistance and resistances in the systemic circuit. So you can imagine, as you can see in this picture here, we have blood leaving the left ventricle and the aorta, and now it encounters resistance. There's very little resistance in the large arteries. But once you get into the smaller arteries, which are muscular, as well as the arterioles, which have smooth muscle associated with them, and then into the capillaries and so forth, there's a lot of resistance. There's quite a bit less resistance in the venous system because the diameters are relatively large, and the pressures are not that high. But what you can see here is, in general, most of the capillary beds are set up so that they're parallel to each other. And this is interesting because it allows for blood flow to be directed from one organ to another. So, for example, if you have vasoconstriction in one set of arterioles, that would lead to less blood flow through a particular capillary bed. And if you have vasodilation at the same time of the arterioles leading to another capillary bed, you'd have an increase in blood flow. Okay, so if we look at this first equation, which is blood flow equals the change in pressure over resistance. If you can imagine, we'd apply this to one of these capillary beds. Well, if there's a decrease in resistance and we have the same pressure, which is going to be our mean arterial pressure, then we'll have an increase in blood flow. If we look at another capillary bed and we say, okay, there's vasoconstriction there, then there's going to be an increase in resistance. Let's say we keep the mean arterial pressure, which is our delta P equal or the same, then that would mean that there's a decrease in blood flow. So we can use this equation to help us understand how blood flow occurs or can change through different organs based on this equation. Now, the other thing we can do with this equation is we can rearrange it. For example, we can multiply both sides by resistance, and now we have delta P equals blood flow multiplied by resistance. So again, remember, delta P is going to be our mean arterial pressure when we're talking about the whole systemic circuit. So mean arterial pressure equals blood flow. Blood flow will be the cardiac output, and then that's multiplied by resistance. In this case, if we're looking at the whole systemic circuit, then it's, instead of resistance, we talk about the total peripheral resistance. I should mention total peripheral resistance is also called total vascular resistance, and it has yet another name, which is systemic vascular resistance. So you'll see it referred to it in multiple different ways like that. Okay, so now that we have this full equation, now we need to go back and try and understand what might happen. Let's say someone's exercising and there's a decrease in resistance in the arterioles going to the skeletal muscle in their arms and legs. Well, this is significant because that's a lot of blood flow that's going to go to the arms and legs as you're running, say. And so this is enough that this will change as those arterioles vasodilate. That's enough of a change that there'll be a decrease in the total peripheral resistance. So recall here we have mean arterial pressure equals cardiac output multiplied by total peripheral resistance. Well, if this goes down, let's imagine for a second that the cardiac output is constant. Then the mean arterial pressure will go down. And so this is a problem, and we'll discuss this in more detail in a second, but this would mean that the person might actually faint because they wouldn't have enough blood pressure to say have enough blood flow to their brain. And so what happens during exercise is that as this peripheral resistance decreases due to the vasodilation of arterioles and the skeletal muscles, there's going to have to be a corresponding increase in blood flow or cardiac output in order to keep the mean arterial pressure constant. And we're going to go through it and look at all this in great detail in the next few slides. This figure shows in a little more detail, again, the basic idea is that the capillary beds are arranged such that they're parallel to each other. But of course, there's some exceptions. One exception is within the kidney. Within the kidney, there's actually two sets of capillaries, and so you'll have blood flowing into one. So you'll have an afferent arteriole that flows into the first capillary bed, and then coming out of that will be an efferent arteriole. Both of these have smooth muscle associated with them, and they can vasoconstrict and vasodilate. and then blood flows to yet another capillary bed before then leaving the kidney. So that's an example where things aren't parallel, but they're sequential. You have one capillary bed followed by another. Now, another example of that, notice for the liver, you do have the hepatic artery that goes directly to the liver. But you also have blood flow from the splenic artery. This goes to the spleen. It then sends blood through the hepatic portal vein to the liver. And then you also have blood coming through the mesenteric artery, which goes to the majority of the gastrointestinal system. And so blood from there goes, again, through the hepatic portal vein and to the liver. This makes sense because, of course, this is a lot of nutrients are picked up by the gastrointestinal tract, perhaps some toxins and so forth also, and those would go next to the liver for processing. The next topic is the regulation of blood flow through an organ. Now, this can be regulated extrinsically, meaning that there's going to be neuronal or hormonal inputs to the organ that will lead to changes in blood flow. It's also possible for an organ to intrinsically regulate its own blood flow by releasing signaling molecules that act in a paracrine fashion by the buildup of metabolites that have a signaling function also, and we'll get into those later. Let's start with the autonomic and endocrine control of blood flow, starting off first with sympathetic nerves. As we know, the sympathetic nerves can increase cardiac output, and we've discussed that before, by increasing heart rate and stroke volume. Sympathetic nerves can also increase the total peripheral resistance. And this occurs through the release of norepinephrine onto smooth muscles of arterioles in the viscera. By viscera, I'm talking about the liver as well as the GI tract. Norepinephrine can also act on arterioles and skin. And in both places, norepinephrine will stimulate the arterioles to vasoconstrict. And this is due to the activation of alpha adrenergic receptors on these targets organs. So here's a diagram of the sympathetic nerves are activated. They release norepinephrine. They act on alpha adrenergic receptors. This leads to vasoconstriction in the skin and the viscera. Now, it turns out actually there are skeletal muscles actually do also have alpha adrenergic receptors. And so sympathetic nervous system is essentially always on. So there is, when you're at rest, there will be some sympathetic release of norepinephrine, and therefore this does lead to essentially tone of these arterioles, or by tone I mean continuous contraction within the skin, within the viscera, as well as within skeletal muscle. Okay, another type of release, and this is going to sound very strange, but the sympathetic nervous system does in fact release acetylcholine in certain selected cases. Normally you associate sympathetic nervous system with norepinephrine and epinephrine. This acetylcholine is released onto skeletal muscles, which results in vasodilations of these tissues. So we can see this in this diagram here. So sympathetic nerves release acetylcholine. They act on muscarinic receptors, and this leads to vasodilation of skeletal muscle. So essentially, we have two different effects here, and they're both activated by the sympathetic nervous system, and yet they have opposite effects. Well, for the most part, this makes sense, though. Like say you have sympathetic nervous system output that increases, and this might be due to exercise or a fight or flight situation. Then you would expect vasoconstriction to the less essential organs such as skin and viscera, and vasodilation to the skeletal muscle. But as I said earlier, there is actually some alpha adrenergic receptors on skeletal muscle, so there is actually some vasoconstriction here. But as it turns out, as you go into an emergency situation or an exercise situation, the balance will change a bit. And so there'll be more release of acetylcholine, and this will cause more vasodilation. And we'll get into it in the next few slides, but there'll be other changes also that lead to more vasodilation in the skeletal muscle, as opposed to vasoconstriction. In the previous slide, we established that norepinephrine released by sympathetic nerves onto viscera and skin leads to the activation of alpha adrenergic receptors, which leads to vasoconstriction. So that would happen in a fight or flight situation. At the same time, we also established that sympathetic nerves onto skeletal muscle release acetylcholine, which activate muscarinic receptors, which leads to vasodilation. Now, in addition to those direct nervous effects, we also have hormonal effects. So sympathetic nervous system activity also leads to activation of the adrenal medulla, which releases epinephrine. Epinephrine then travels as a hormone throughout the circulatory system. It then binds to beta adrenergic receptors, which leads to vasodilation of skeletal muscle. So this is an additional factor that leads to vasodilation of the skeletal muscle, which prepares the body for a fight or flight situation, or also during a less extreme situation, if you're, say, exercising, you'd have some release of adrenaline, and this would also lead to vasodilation of skeletal muscle. Therefore, during fight or flight, blood flow is increased to skeletal muscle, and during fight or flight, blood flow is decreased to skin and viscera. Again, that was on the previous slide. That was due to the effect of norepinephrine acting on alpha adrenergic receptors in the skin and the viscera. The decrease in blood flow to the skin is often puzzling to students because they think, oh, well, when someone's angry, doesn't their face turn red? Well, actually, it's the opposite. In the very first instant, when someone's either extremely frightened or extremely angry, the blood actually drains out of their face, and they actually take on this very pale complexion. And that's actually the original sense of the word livid. So livid would mean has a sense of ashen or pallid, meaning a very light complexion. And so this happens when the blood drains out of the skin, and it goes to the heart, to the brain, to the skeletal muscle to prepare someone for a fight or flight situation. Now, we sort of take it to mean the opposite nowadays, because often after, say, the fight is over, or after someone's had this really scary situation, but now they've saved themselves, then the blood then rushes back to the skin, and they have this much more red or flushed complexion at that point. So overall, the control of regulation of blood flow is probably mostly done by the sympathetic nervous system. But the parasympathetic nervous system does, in fact, have an effect, and the way it does this is by releasing acetylcholine at various synapses. So acetylcholine stimulates vasodilation. And if you think about the whole idea of rest and digest, which is the opposite of fight or flight, in a rest or digest situation, you're having a good meal, or you're anticipating a good meal, and therefore you're going to have more blood flow to the digestive tract and the salivary glands. And of course, having a good meal and being relaxed may lead to other things if you're with a partner or something like that. And so there may be more blood flow going to the external genitalia. And so that's really just the main things that the parasympathetic nervous system regulates in terms of blood flow. And so acetylcholine acting on muscarinic receptors leads to vasodilation in the digestive tract, the external genitalia, and the salivary glands. But as I said, again, it's just not as big an effect as the sympathetic nervous system. These are important for just a very select group of things. When you're resting and digesting, then you would have increased blood flow, and this would in fact be helped by the parasympathetic nervous system. So far, we've discussed extrinsic factors that affect blood flow, but there are also intrinsic factors. One type of intrinsic factor is paracrine signaling molecules that are released by cells within a tissue that control other cells within the same organ. So, for example, in this context, the tunica interna, which is the endothelial layer, as well as some fibers of collagen and elastin. This tunica interna can release certain signaling molecules. So, for example, it can release bradykinin, nitric oxide, prostaglandin I2, and all these signaling molecules lead to vasodilation by leading to relaxation of the smooth muscle, which is in the next layer, the tunica media. The endothelial cells can also release endothelin 1, which stimulates smooth muscle contraction and produces vasoconstriction. A quick note is that your book considers these paracrine regulatory signaling molecules to be extrinsic, I suppose because the signals are coming from cells outside of the cells that are being affected. I simply group them together with intrinsic because it's all within the same organ. But really, there's not much difference. It just, these are, in both cases, we're talking about local control by paracrine signaling. Okay, I'll briefly recap what we've been talking about using this table from your book. When we have sympathetic nervous activity acting on alpha adrenergic receptors, we get vasoconstriction. And this occurs more or less throughout the entire body. So this is a very large effect. So generally, the sympathetic nervous system will lead to vasoconstriction. Now, there are beta adrenergic receptors. And so norepinephrine and epinephrine acting on these receptors can lead to vasodilation. So, for example, within skeletal muscles as well as coronary blood vessels, you can have vasodilation if there's a lot of, say, epinephrine. But normally when a person's at rest, skeletal muscle and coronary vessels also have alpha receptors, alpha adrenergic receptors. And so in general, when a person's at rest, the alpha adrenergic receptor mediated effect, which is vasoconstriction, is dominant. Okay, now we also have the release of acetylcholine, which causes vasodilation. And that's, again, still released from the sympathetic nerve fibers. This can lead to localized effects in arterioles of skeletal muscle. And this would generally be produced in an extreme situation, such as a fight or flight situation, or maybe intense exercise. That's it for the sympathetic nervous system. Now, if we look at the parasympathetic nervous system, we see that it leads to vasodilation through the release of acetylcholine acting on muscarinic receptors. Now, these effects are really quite limited. They're just limited to the gastrointestinal tract, the external genitalia, and the salivary glands. And because it's so restricted, it has a relatively small effect on the total peripheral resistance. Now, these other things are hormones. Angiotensin II leads to vasoconstriction, and this may help to increase the mean arterial pressure, which helps with filtration pressure in the kidneys. ADH is antidiuretic hormone. We talked about it before, I believe, with respect to reabsorption of water in the kidney. It also has a vasopressive effect, meaning that it increases blood pressure, and it does this through vasoconstriction. Although the concentration of ADH that's needed to have this effect is much greater than the concentration needed for the effect on the kidney. Histamine leads to vasodilation. Histamine, as you know, is related to the inflammation reaction. So say you scratched yourself, you get a localized vasodilation near the scratch and there's increased blood flow there. Histamine is also involved in allergic reactions. Bradykinins, we just talked about. These are released as paracrine signals, and they can lead to vasodilation. And prostaglandins also can be released in a paracrine fashion, acting locally within a tissue, and they can lead to vasodilation or vasoconstriction. As I mentioned earlier, the mean arterial pressure is really important because it serves as the potential energy which drives movement of blood through an organ. So if the mean arterial pressure is too low, that could be problematic because there might not be enough force for perfusion. And if it's too high, this could damage organs also. So by certain organs, you have certain organs in your body have autoregulation of blood flow. So this is used by the brain and the kidneys. And this promotes constant blood flow when there's fluctuation in blood pressure. So this autoregulation is based on the idea that the muscle itself, so the vascular smooth muscle, responds to changes in arterial pressure. And so this is considered to be a myogenic response. Myogenic, myo refers to muscle, and genic means it's given birth to or generated by the muscle itself. So let's use the example of your brain, which is very sensitive to blood flow. Let's imagine there's a decrease in blood pressure, and this could be bad because this would mean that you might not have enough blood flow to your brain and you might then faint. but you actually have this autoregulatory mechanism with your brain. So when you have a decrease in blood pressure which is detected by the smooth muscle in the cerebral blood vessels, then the cerebral blood vessels will dilate, thereby increasing flow through the brain, preventing you from fainting. What about the opposite situation? Let's imagine that your blood pressure increases so much that it could, potentially cause damage or bursting of cerebral blood vessels, which are very delicate. Well, in the response to an increase in blood pressure, the smooth muscle will detect this change in pressure, and they'll respond by constricting, thereby reducing the amount of blood flowing through these delicate blood vessels in the brain, and thereby protecting your brain from damage. In addition to stretch, the smooth muscle that encircles arterioles may also respond to certain local cues within an active organ. So if we take the example of active skeletal muscle, then there may be, for example, vasodilation in response to a decreased oxygen concentration. So skeletal muscle is able to use up oxygen through aerobic metabolism, and this may indicate that there should be an increase in blood flow to that particular skeletal muscle, and therefore vasodilation would help with that. At the same time, other signals will also indicate that there should be an increased blood flow to a particular capillary bed, such as an increase in carbon dioxide concentration. Again, would be a waste product of aerobic metabolism. There may be a local decrease in pH, so this means there's an increase in hydrogen ion concentration. This would happen in response to an increase in CO2 production locally, so that's again an indicator of aerobic metabolism. Hydrogen ion concentration will also increase in response to lactic acid coming out of, say, skeletal muscle due to anaerobic metabolism. Additionally, when muscle is very active, it may release potassium, and there may also be paracrine signals, such as nitric oxide released by endothelial cells within the blood vessels themselves. And there's a host of other chemicals, such as adenosine, that will also have the effect of leading to vasodilation. So the basic take-home message is there's a lot of things here that can all indicate that a muscle is very active metabolically, and therefore there should be increased blood flow to that particular muscle. So this brings us to the next topic, which is types of hyperemia. So hyperemia means hyper means there's excess blood flow. So reactive hyperemia is due to a constriction, which causes a buildup of these metabolic wastes that I just mentioned in the previous slide. So an example of that is you could say cut off circulation to a finger. So if you do this for long enough and then you release your grip on the finger, then you'll see that the finger will get a little bit flushed with blood, and so it'll have a reddish tinge to it. And that's because what happened during the occlusion is you prevented blood flow, and therefore there's going to be a buildup of CO2. The pH will decrease. There'll be a buildup of adenosine. There might be a buildup of nitric oxide, and so forth. And so as soon as you release the pressure on, say, the finger or the hand, then there's suddenly going to be blood flow to the finger or the hand, and then that is reactive hyperemia. It's an increased blood flow in response to this increase in metabolic wastes and signaling molecules. Another type of hyperemia occurs when you're exercising. So say you're very active, and that would then, like your skeletal muscle, say you're running or something like that, that would increase the generation of nitric oxide, of adenosine. It would increase potassium levels within the muscle. It would decrease pH, meaning there's an increase in hydrogen ion concentration for the reasons I discussed earlier in the previous slide. And so all of these things would lead to an increase in blood flow. And that again could make, if you had this in the skin, it would lead to a more reddish tinge in the skin. So I should mention this active hyperemia is actually incredibly important. It's one of the ways that you control blood flow to specific muscles. So let's imagine that you're doing an exercise that involves exercising the arms but not the legs. Well, it wouldn't really make sense to have a lot of blood flow to the legs at that point, right? And so through this process of autoregulation with intrinsically varying the blood flow to specific muscles that are active, then you get the blood flow to where it's needed and not just a general increase in blood flow. The next topic is blood flow to the heart and skeletal muscles. Your heart works primarily through aerobic respiration. It does have some ability to do anaerobic respiration, but it's very limited. So the coronary arteries supply blood in massive number of capillaries to the heart. And in fact, the density of capillaries is extremely high. It's higher than in most other organs. And for this reason, each myocardial cell is within 10 micrometers of a capillary. In other tissues, say skeletal muscle, you might have a larger distance of, say, 70 microns between a capillary and a cell. Contraction during systole squeezes the myocardium, and this actually restricts blood flow. This means that cardiac tissue receives blood primarily during diastole and not during systole. And in order for that to work, the cardiac tissue has a very high amount of myoglobin in it. So each cell has myoglobin. Myoglobin is an iron and oxygen binding protein, and it's similar in some ways to hemoglobin in the sense that it oxygen binds. Myoglobin happens to have a higher affinity for oxygen than hemoglobin. So it acts sort of like a shuttle. Like the oxygen leaves the hemoglobin, comes through the capillary, through the interstitial space, it enters into the cell, and there it can be sort of temporarily stored on myoglobin. And then the myoglobin is able to give up the oxygen, which then is used in the mitochondria within the cardiac tissue. And so it serves as a sort of temporary store during diastole, and then it's released during systole when there's effectively very little blood flow through the capillaries in the myocardium. So almost all ATP is produced by aerobic respiration, and it's primarily produced by the oxidation of fatty acid, glucose, and lactate. The metabolic rate of the heart can change dramatically depending on whether you're resting or exercising. When you're at rest, norepinephrine released from sympathetic nerve fibers acts on alpha adrenergic receptors, and this stimulates vasoconstriction. So this raises the vascular resistance and it limits the blood flow through the coronary arteries. Now, in another situation, say you're exercising intensely or you have a fight or flight response, then the adrenal glands release epinephrine. Epinephrine acts as a hormone on beta-adrenergic receptors within the smooth muscle that encircles the arterioles within the coronary arteries. And this then stimulates vasodilation, and this decreases vascular resistance and thereby increasing blood flow during exercise or fight or flight situation. Finally, once you start exercising, then you'll have a rise in certain metabolic waste products such as CO2. You'll have potassium. You'll also have the generation of paracrine regulators such as nitric oxide. And all of these are very powerful stimulators of vasodilation. And so that will also increase blood flow during exercise. In order to assess the health of the coronary arteries, an angiogram can be performed. This is a standard method for assessing coronary artery disease. To do an angiogram, a catheter is inserted through a brachial artery or another major artery, and it's threaded all the way to the heart. And then a electron-dense dye, such as iodine, is injected into the coronary arteries. And then a technique called fluoroscopy is used to image in real time the interior of the heart. This is a picture of an angiogram here showing a site of obstruction. So an angiogram is an X-ray picture with a contrast dye. An angiogram of the coronary arteries might reveal narrowing caused by atherosclerotic plaques, a thrombus, which is a type of stationary blood clot, or it could be a spasm. A a coronary artery spasm is a sudden tightening of the muscle within the arteries of the heart. And this can actually prevent blood flow to your heart and also cause a heart attack. If a coronary artery is blocked, a coronary angioplasty may be performed. This consists of inserting a catheter with a balloon into the occluded site of the coronary artery and then inflating the balloon to push the artery open. In some cases, stents are inserted also to support the open section of the coronary artery. Another kind of operation is the coronary artery bypass surgery, in which is the most common type of open heart surgery that's performed. This involves grafting of a blood vessel taken from the patient, typically from the leg, onto the aorta, so that it bypasses the narrowed coronary artery. So even in people that have had heart attacks, sometimes exercise has been recommended. So exercise training has a lot of beneficial effects. One is an increased density of coronary arterioles and capillaries. Another is increased production of nitric oxide, which promotes vasodilation. And thirdly, there's an increased compression of the coronary arteries during systole due to a lower cardiac rate. So this last one I should explain a little bit. So if the cardiac rate is lower, then there's less time spent in systole, and therefore less compression of the coronary arteries, and this allows for more blood flow. We'll next look at the regulation of blood flow through skeletal muscles. So when a person is at rest, the arterioles have a high vascular resistance, and this is due to alpha adrenergic sympathetic stimulation. So if we look at this diagram here, we can see that the person's at rest, the sympathetic nervous system is active to some degree. They're releasing norepinephrine, which has an effect on alpha adrenergic receptors, which is to vasoconstrict the arterioles and skin and viscera to some degree, and also to lead to vasoconstriction of skeletal muscle. Despite this sort of tonic vasoconstriction, even at rest, skeletal muscles still receive about 20 to 25% of the body's blood supply. And that's simply because there is so much of it. The skeletal muscle makes up a certain fairly large percentage of the total body mass. Now, one thing you may have noticed is when you're exercising, there are certain exercises that can be very fatiguing and actually almost painful. Typically, for example, if you do an isometric contraction of a muscle, so let's say you've contracted the muscle beyond 70% of its maximal contraction, well, that actually stops the blood flow through it squeezes on the muscle and it stops the blood flow through the capillaries. And so then that can lead to fatigue and pain. Let's now look at what happens when a person begins exercise, or even just before the beginning of an actual exercise, when they're anticipating the beginning of an exercise. In this situation, you'll still have the original norepinephrine release due to sympathetic fibers acting on alpha adrenergic receptors, leading to vasoconstriction. But now additionally, you'll have vasodilation. And one reason for this is that sympathetic nerves, certain ones will release acetylcholine, and acetylcholine acts on muscarinic receptors, leading to vasodilation in skeletal muscle. Now, additionally, you'll have sympathetic activity leading to the activation of the adrenal medulla, which releases epinephrine. And then that acts as a hormone on beta adrenergic receptors, which leads to vasodilation of skeletal muscle. So overall, you're starting to shift the balance from vasoconstriction, which is actually due to the sympathetic nervous system, to now the sympathetic nervous system shifting towards effects which involve vasodilation. In addition to this, once you actually start exercising, then we talked about autoregulation earlier, there are intrinsic metabolic controls that enhance vasodilation during exercise. Now imagine that our person is doing a much heavier exercise, a fairly intense exercise. At this point, there's a decrease in the alpha adrenergic activity. So I've removed that from the slide. And now we're just seeing an increase in cholinergic sympathetic activity, which leads to vasodilation in the skeletal muscles. At the same time, we still have perhaps even more release of epinephrine if this person is exercising very intensely, again, acting on beta-adrenergic receptors, leading to vasodilation of skeletal muscle. And on top of those two effects, we still have a buildup of metabolites intrinsically within the muscle that are leading to vasodilation. Again, those are effects such as the release of norepinephrine, adenosine, an increase in metabolites such as potassium, hydrogen ion, a decrease in oxygen, and increase in CO2, all within the tissue. And it turns out of all these effects, that's actually the biggest one. So once someone's really, exercising really strongly, these intrinsic metabolic controls are really have the biggest effect in terms of leading to vasodilation and increased blood flow to active muscle. So we'll end this lecture on this table, which summarizes what we've been talking about. When a person is at rest, they'll have a certain amount of blood flow to skeletal muscle, let's say 1,000 milliliters per minute. And the reason for this is we have high adrenergic sympathetic stimulation of the vascular alpha receptors, and this causes vasoconstriction. So we don't really need that much blood flow, and so the resting blood flow rate is relatively small. Now, as the person begins to exercise, or even in anticipation of exercise, there's going to be dilation of the arterioles and skeletal muscle. And we talked about this being due to the cholinergic sympathetic nerve activity, and then also stimulation of the beta-adrenergic receptors by epinephrine. And finally, once a person's really exercising very intensely or heavily, now notice the blood flow rate is increased tremendously by a factor of 20. And in this case, we have a fall in the alpha adrenergic activity, which was causing the vasoconstriction. We have an increase in cholinergic sympathetic activity, which causes vasodilation in skeletal muscle. And we also, within the active skeletal muscles, have autoregulation in the sense that we have increased metabolic rate of exercising muscles, which produces metabolites as well as paracrine signals that lead to vasodilation due to the relaxation of the smooth muscle encircling the arterioles within the muscle. Okay, so we'll end there.